Hi, my name is Mike Heroux. I am the Director of Software Technology for the U.S. Exascale Computing Project, also a senior scientist at Sandia National Laboratories, and the PI of a post-ECP project called PESO that you will hear about a bit today as well. The first thing I'd like to chat about is ECP's impact, in particular in the portable libraries and tools for accelerators. One of the big efforts within ECP was the software technology portfolio, the creation of that. And that effort was broken down into 6 technical areas. And I'll talk about each of those a little bit as we go through the presentation. The first is the programming models and runtimes, and I'll let you read the details in the slides. Development tools, math libraries, and data and visualization. And then software ecosystem, which is a relatively new focus area for DOE software libraries and tools as a collective. And then the 6th area is the NNSA software technology activities. And these are the open source libraries and tools that intersect with Office of Science user bases and are important to integrate into the broader DOE software ecosystem. In fact, some of the examples I'm going to show you just now actually are funded by both the Department of Energy's Office of Science and by the NNSA. And they have a broad funding and user base. All right, so a little bit about the portfolio. This is a bit of a sketch. And so some of the key themes were a focus on GPU node architectures, advanced memory and storage technologies. And our goal was to create a new highly concurrent, latency tolerant collection of libraries and tools based on new algorithms. We had to do this not just for NVIDIA GPUs, which were a common focus in the past, but also for Intel and AMD GPUs. And to enable the access and use of these libraries and tools via standard interfaces. We had 3 basic categories of software. One was next generation versions of the products that are widely used, things like MPI-CH, OpenMPI, and PETC. And also what at the time were emerging products, things like Cocos, Raja, Ginkgo, and SPAC. Were known by some people in the community, but during the lifespan of ECP became critical components of the software ecosystem. And then others were really quite new. And Variorum, for example, is one I'll show, in ZFP are brand new products, winners of last year's R&D 100 award, as were some of the other products within ECP a few years before. And then you can see kind of a set of sample example products. The MPIs, 2 of them we sponsored efforts for. OpenMP, OpenACC, kind of markup based versions of delivering on no parallelism. The C++ performance portability abstractions, things like Cocos and Raja. We also made a lot of contributions to LLVM and vendor compilers through our efforts, emphasizing features that were most important for HPC and that might not otherwise get the kind of attention by the broader community. Performance tools, especially those at scale, and then math libraries, which have been very successfully funded by DOE for many years, transforming those to be performance portable across the 3 GPU architectures that we had to support. And then I/O, HDF5, MPI/I/O, Audios are all on to next generation versions to handle the advanced I/O subsystems that were on these large scale systems, and to mitigate the ever increasing performance gap between what happens in the computational phase, what happens in the data motion phase through memory, and then what happens to the I/O subsystems. The gap between and performance between all those 3 layers continues to expand as we go forward. So we have to invest more in latency hiding techniques in these libraries. And then in the data and viz area, peer review related products and development, and a few other things as well. So the legacy of ECP is this stack, one of them at least. One big legacy of ECP is this stack. that enables performance portable application development on leadership platforms. You can truly write a high performance computing application on top of the stack that ECP developed, um, that is not only portable across all the GPUs and CPU architectures, including ARM-based processors, but also performance portable, and that you can get scalable performance on all of these GPU architectures. You might have to, for say, a particularly performance hotspot, do custom versions of a few kernels, but generally speaking, you can live in this performance portable space and do quite well. So I'm going to talk a little bit about the four areas that I mentioned, four of the six in the earlier slide. I'll talk in the programming models and runtimes area about our efforts to do performance portable libraries and tools that support applications so that they can write performance portable applications. There are a few basic approaches. One is GPU-specific kernels. Some teams did that, where they wrote a specific kernel for each of the types of GPUs. This is a difficult approach long-term, and because you have to continue to write new versions of every single kernel. Loop pragma models based on OpenMP and OpenACC are also possible. In our experience, those tended to lag the availability of other capabilities because the compilers weren't catching up quickly enough with the available hardware, and the vendor stack was not ready to support these markup languages quick enough for ECP. Now, if you're coming in later after things are established, you can rely on them, but we couldn't very easily rely on them. So then the two most important ones were our C++ abstractions. This is in particular Cocos and Raja, which were available and ported, first and foremost to the new platforms. And then the co-design frameworks. These are things like SEED and AMRX, which in turn actually built on top of many of these C++ abstraction layers, but they also provided portability for the applications that built on top of these. So these are the four ways that teams picked for getting performance portability across all these various architectures. And this just shows, a distribution of how the user base, and it showed in general that teams tended to migrate as they were able to C++ from Fortran, and how they tended to utilize the Cocos and Raja and the co-design approaches. Although certainly, of course, there were some native GPU and some loop pragma activities. Also, as time went on, this is from 2022 when the survey was done, we saw the migration proceed even further, towards C++ and toward Cocos, Raja, and the co-design libraries. So a little bit about development tools. I won't go into, I'll give you just one example from this space. And this is Variorum, but it exemplifies one of the basic patterns of the development tools that we sponsored under ECP, and that there's a lot of different hardware, and there are many users of that hardware, and each type of user wants a different functionality or different perspective on the available hardware and system software. And Variorum is a good example of that because it abstracts away the vendor details for a cross-cut of various architectures. And so you can look at all of those architectures through a common concept-oriented interface. And then furthermore, it has specific types of API features that system administrators want, that application scientists want, and that research software engineers want. And so it provides multiple ways of aggregating capabilities and abstracting away details that are not fundamentally important for the users of the system. Again, our Variorum won an R&D 100 award in 2023 as a tool that was very valuable to a lot of people. Variorum is platform agnostic, vendor neutral, simple front-facing APIs. And also the team has done the work of integrating with lots of other libraries and tool capabilities, and then supporting this on the Exascale platforms and many other type of architectures. So it's a really nice example in the tools space. In the math libraries area, again, we have lots of efforts that went on under ECP. One of them was to develop a new class of sparse solvers for a problem domain that's not commonly been covered by DOE activities in systems engineering domain. So one of the things they have is a type of system. It's a Kurushkuntung formulation, KKT, formulation that ends up generating a series of sparse, symmetric, indefinite problems. And those problems need to be solved repeatedly. Now, within the existing solver stack, in particular within the SuperLU project team, there was existing functionality that could be generalized to handle this kind of system. Then the Ginkgo team had a software architecture that could take in the new algorithms from SuperLU, and then together those two teams work with the ExaSGD project to create this new kind of solver for this kind of problem. And the result is a nice performance portable, first of a kind solver in this space that is highly competitive with vendor offerings in this space. The MA57 Ku solver is NVIDIA solver base, and then Ginkgo, shown here on the two right columns, was very competitive and is performance portable across all of the GPU and CPU systems. And so it's another example of some of the nice work that's been done. And it also is similar to other work in the libraries area in that way. In the data and visualization space, I mentioned how there's this growing gap between the raw speeds and feeds of data systems versus memory versus compute. And ZFP is one response to this issue in that it provides compressed multidimensional array primitives that are user callable to allow someone to compress the actual storage of data in lossy or lossless forms, but with control. And so they're able to store less data in arrays, in memory, write them out to disk if they need to, read them back in, and in a abstract way, increase the performance of memory and data storage through this kind of compression technology. Again, this team has gone through all the effort to make sure that the tool is available in supported robust ways across all of the Exascale platforms, and it's used in a variety of I/O products under the hood. And many more. There are lots of libraries and tools capabilities that were sponsored by the ECP. We sponsor 70 products altogether, contributions to those products, and then many more benefited from the interactions with the teams who are creating these new capabilities under ECP. Okay, so that's a little bit about the individual libraries and tools. Let me talk a little bit now about the software ecosystem and the legacy that we foresee from that, being in particular E4S and SPAC. So for decades, DOE has delivered high quality, reusable libraries and tools, things like PETSI, things like the MPI-CH OpenMPI, things like HPC Toolkit, just a few examples. So that is not new. What is new is the aggregation, the community building that we've been doing under ECP and that we foresee as a long-term impact of our activities. In particular, what we call SDKs, are collections of teams. It's a team of teams concept where people who are working on the same kind of software capabilities, math libraries, IO libraries, they aggregate together in a way that's community building. They can identify common needs, common capabilities, complementarities that they want to pursue. They can identify policies to improve software quality, learn from each other as part of that. That is started a bit before ECP, but continued on very strongly within ECP from the same teams of people that were working on it before ECP started. Something that's brand new under ECP is E4S, which is the aggregation of everything. It's the curated portfolio of software capabilities. As I said, we sponsored 70 products from ECP, and we needed a way to distribute those. E4S is that way that we distribute all of these software capabilities. Furthermore, we include many more, including AI support, supported libraries for that community. In total, roughly about 20 directly supported software libraries and tools are part of E4S, plus hundreds more that we build using SPAC's dependency management capabilities. So E4S is this curated stack. We do quarterly releases of E4S. The latest was in February, this past few months ago. We have a collection of community policies, which are our commitments to software quality. We curate this so that everything is version compatible. We provide a doc portal that's a single point of access to all the documentation for the supported products. We do quarterly releases. You can go find out about everything about E4S at e4s.io, the website. And increasingly, this is a turnkey stack that people can use it. We do a lot of portfolio testing, and E4S has emerged within the vendor community as a good proxy for an HPC software stack. And so if a vendor, let's say an NVIDIA or Intel or Google, want to have a representative software stack, so if they're preparing for a release of their own HPC software capabilities, E4S is increasingly a nice proxy for all of HPC. So they can test all of their product pre-release against the public version of E4S and better assure that when they do a release of their own products, that it'll be compatible and consistent. There'll be fewer surprises in the broader HPC ecosystem. As I mentioned, we also include AI capabilities, PyTorch, TensorFlow, Horovod. We also include the co-design libraries, AMRX, Cabana, and MFEM as a part of this. So E4S is one of the big legacies coming out of ECP that will continue on in the future. I'll mention also briefly one of the interesting emerging resources that ECP supported, and we foresee continuing, is a system we call Frankenstein. That is a collection of dozens of different device types, all sorts of CPUs and their related software stack, many GPUs and all their related software capabilities. And then now recently Grace and Grace Hopper nodes. And what we do with Frank is we provide the latest hardware we can get access to and the latest publicly accessible software stack. So Frank exists as a workhorse for doing porting of software capabilities. We have one massive shared file system that has access to all of these node types. And so you can clone your library or tool, PETSI, for example. You can clone it on this file system and then build it on all of these different node types. And better assure that everything will work the way you expected on all these different node types. And then and that's a preparation for the leadership class systems, which certainly have early access node architectures. Aurora, Frontier, El Capitan have early access node types, but it's usually with non-release software and stuff that is non-disclosure agreement restricted, and so not everybody can get access to it. And furthermore, these are very highly utilized resources, and they can't be used for things like continuous integration testing. Frank can be. We've done millions and millions of continuous integration tests and builds on Frank, and it's been an incredible resource for us in our efforts. And we foresee this as an emerging best practice for reusable libraries and tools in the future. And these are just a few examples of other things that we've added to Frank as time has gone on. We also mentioned that there's an E4S Pro image. This is a version of E4S that's available on the Amazon AWS Marketplace and can be supported by a commercial partnership that we have with Paratools. And I'll talk a little bit more about that in a moment. Okay, and this is the time. And so what the other thing we evolved with ECP that we foresee continuing is our business model. So when ECP got started, there was, if you were a user at a local facility, say you were a user at Argonne National Lab, you were using resources at Argonne's leadership computing facility, you could generally rely on and interact with the team has libraries and tools at Argonne. Now you can, certainly there were other interactions you could have, but that was the dominant, I'm going to use the libraries and tools available from my lab on my system. ECP enabled a cross-facility, cross-lab trust model where if you were at one lab and wanted to use libraries and tools from a team in another lab on a leadership computing system at another lab, you could do that because ECP was a large multi-lab, multi-institutional effort, and there was this expansion of trust across all the facilities and development teams. That was the first phase of optimizing cost and benefit sharing. The second phase was being able to do that with other US agencies and industrial users. And that happens because we now have this relationship with paratools that can support E4S users who are outside of DOE. In fact, paratools also supports users at the facilities through a special contract that allows them to, if someone has an issue with an E4S product, they can go to the paratools team and help to debug and create a reproducer and find the development team that can fix the problem if that's required. And then paratools and then also kitware is a part of this picture, also allows teams outside of DOE to utilize E4S and trust that if they like the products and want to use them, there's a commercial support option available to them that they can pay for, and they're happy to pay for that support. Where the DOE lab scientists couldn't necessarily do this. It's part of our mission to help people get started, but we're not long-term support staff for people outside of the DOE. And so this commercial partnership with paratools is the mechanism that we have for expanding the support of E4S for people who are outside of DOE. So you can see this expansion of cost and benefit sharing that occurred during ECP. The last and very promising new approach for cost and benefit sharing is the High Performance Software Foundation. And I'll talk about that next. So the High Performance Software Foundation is a brand new umbrella foundation under the Linux Foundation that is focused on fostering a software ecosystem for high performance computing. It was announced originally at Supercomputing 2023 in Denver. There will be further announcements at the ISC conference coming in a few weeks. I'm talking here in April of 2024 and May of 2024. There will be announcements of further progress, initial projects that are part of that. And this is emerging as an incredibly valuable and rapidly evolving way to increase, again, the cost and benefit sharing of these open source libraries and tools. And we foresee that this is creating a very robust, well-financed way of supporting teams that do library and tool development for high performance computing and expanding the user base and expanding the contributions to those new products. There's lots of win-win-win type of arrangements that are emerging from HPSF that complement what's also going on within E4S. So a little bit of a summary. So all the ECP libraries and tools are being actively supported on Exascale platforms. They also work on an array of other platforms, every commonly used processor type. Frank Cluster I mentioned has a couple of Grace and Grace Hopper nodes, and most of the ECP software technology products work on these. The use of these portability layers that we've worked on, lots of products are already poised to work on future platforms. So there are new emerging architectures, things like data flow architectures. We're already really well positioned to have a running start on those. Of course, we need to optimize a bit more, but we're well along the way to being ready for those, even though they're not available for us to work on. Libraries also support applications regardless of what GPU programming model the apps use. This is a subtle point, but basically it says an application team is free to choose whatever GPU programming model they want, and our libraries and tools can adapt to their choice. Performance portability is generally available, sometimes with a modest slowdown, but you can always customize just a handful of kernels that need it. It's still a huge win in productivity. And then the final point is HPSF will provide even greater cost and benefit sharing as we go forward. All right, so just a bit of a summary. So E4S is, one of the most important legacies of ECP, in my opinion. It's a large, scalable, curated product portfolio. It includes a lot of existing AI products, and we foresee that it will include future ones, especially as ML becomes a huge part of the scientific ecosystem, even more than it is already. Um, Quantum processors, we don't know what they'll exactly be like or what their software stacks will look like, but we have the infrastructure in place already for accelerators. And we think, quantum processors will very likely be a kind of accelerator like GPUs. And we have the software infrastructure in place to support accelerators and their custom software environments. And we view that as extensible to quantum processors. Our community policies drive quality. We foresee that continuing. The Frank system is an essential resource for us as we prepare for and maintain the quality of our software on a large variety of node types. We build on SPAC, and this is the backbone for much of HPC software going forward. And the flexible business models we created under ECP should continue to make our software available and with optimal cost and benefit sharing. And all of this is central to post-ECP efforts. So let's do some final thoughts on E4S. Does it contain too much? Yeah, it's got 120 plus products plus 100 other derived dependencies. Few people use everything. Does it not contain enough? Yeah, most serious users want products that are not part of E4S, but they can get them via SPAC. Increasingly, almost every HPC product is available with some kind of SPAC build. Is E4S ported and tested on too many configurations? Yeah, I think most users only need a few. Is it not ported and tested? Yes, almost everyone needs to tweak it for their environment. So then if all of these things are true, is it still useful? And I think it's still a big yes. And the reason for that is that E4S and all the builds that we do for all the platforms, for all the products, even though it's not enough and too much, means that what any particular user wants is only a delta away from what we do already. And it is certainly a much better starting point than if they had to manually curate and manage their own stack. And that, I think, is the tremendous value proposition that E4S provides. Okay, let's talk a little bit about lessons learned. ECP was a big project. We did a lot of stuff, some of it, for the first time. And so there are some things that we took away from this. So what are some of them? Integrations lesson learned. So the concept of capability integrations, which is, we focused in our success metrics for ECP is a library being used by an application in a sustainable way and demonstrated in the Exascale environment. It turned out that that kind of metric pushed people very hard. It was difficult to achieve, but it was incredibly valuable. And it made sure that the work that we were doing would have a life after ECP was done. Now, KPP3, the key performance parameter that was used by the software technology area was a lot of work, and it was unusual work for our teams and reviewers. We had to do a lot of training of our teams and of the reviewers in order for them to understand exactly what kind of process we were undertaking. Now, going forward, after having socialized this approach with teams, it'll be easier going forward. But it was a lot of work, and so more than we anticipated. Some of the important elements to success with the integration activities was we brought in an integration lead and deputy as part of the project, and we also have project coordinators for each of the products. So this is a person who is familiar with the process that ECP was imposing on teams and could, in a sense, be the expert. PIs were not always the best people at process. They were focused on developing new algorithms, developing capabilities, and process is somewhat orthogonal to that. So bringing in and populating expertise across the organization was an important success element. Also, as I mentioned, Frank, we also, of course, had other systems, early access systems that were essential to getting our work done. And it led to this stack being the most stable on Frontier. For example, the most stable software and application portfolio ever based on any other system that's been installed at Oak Ridge prior to that. So the spin up of Frontier and the spin up of the software and applications on the Frontier had the best success ratio from in the very beginning than ever before. The last thing I'll mention is we had shared fate milestones. The KPP3 was a shared fate. The application and the library or tool team were in it together. We managed those, and we had an integration database that helped us manage those relationships, and these were essential to our success. Some other software ecosystem lessons learned. We found that this hierarchical kind of process-driven approach to scientific library and tool development, it can work. And in fact, I think, when we were doing this heavy lift to portable GPU libraries and tools, it really was an essential approach that we could, collectively plan and execute and assess. So, planning, execute, track, and assess. That was a basic process on a, quarterly and annual basis. That was essential to our success in this time of rapid introduction of new features. One of the things in this space that we learned after the fact was, not having no coordinated post-ECP plan was a challenge especially for the leadership team. We needed to deliver our final integrations, KPP3 results, but many of our teams were distracted during the final year because there was no coordinated post-ECP plan in place. And so team members were pursuing what they would do after ECP. And some of them, because an opportunity had arisen, left before the final end of the ECP. And so lots of teams were, had thin staffing. We fortunately were able to accomplish everything we needed to do, but it required a fair bit of activity on the part of the leadership teams to make sure that we could accomplish what was required to be done. Another lesson learned in the software ecosystem is that software as a facility or consortium has promise. You'll see in a few slides here the creation of a consortium that's intended to carry on this aggregation that we did under ECP, a little bit looser, with more spread out leadership, but still with the intent that we're better as a collective than we are individually. And that's what we're trying to do in the post-ECP era as well. A few other things, ECP is a construction project, a tailored earned value management system, provided a clear process for software governance. And although I don't anticipate with post-ECP we're going to do anything quite as formal, at least not for a while, we learned a lot about how to do cost scope and budget management. And so it was very useful for us for building up processes for doing reviews, for coaching underperforming teams, for off-ramping chronically misaligned or underperforming projects, to identify gaps and fill those gaps, and then to iteratively plan, execute, track, and assess towards goals. And it allowed us to holistically scope, the libraries and tools efforts and make them a first-class entity in the HPC software ecosystem. And we foresee this kind of sensibility going forward in the future in post-ECP. Okay, a little bit about performance portability lessons learned. Node-level performance portability is possible. In particular, library approaches like Cocos and Raja, others, of course, can work well. And we are in much better shape today than 7 years ago in providing capabilities for an application team who wants to run on portably across and performance portably across a bunch of different architectures. This is a huge benefit from the ECP investments. And library support for diverse application programming models choices is also possible. I mentioned that already. And then, in general, ECP investments in node parallel algorithms, libraries, and tools have had a broad impact. And this will continue to be benefiting many, many people as we go forward. So summary in this part, ECP has made a lot of contributions to software technology has made a lot of contributions to the success of ECP. We've established this new way to measure contributions of libraries and tools. KPP3 not only measured success, it drove collaboration. Again, the shared fate was a huge part. It spurred better software practices. Teams were incentivized to invest in usability and support, which improves the long-term, cost and benefit sharing. And then we guided portfolio management, off and on-ramping and scope changes. We actively managed our budgets, and we learned and recorded many other lessons for the future. All right, so let's go forward a little bit in the last part of this presentation. So post-ECP, the Department of Energy's Office of Advanced Scientific Computing Research, we call it OSCAR, funded these seedling projects. And these are small efforts started a year or so ago that allowed us to start exploring what might happen after ECP is over. And I won't go, I'll leave these slides for you to read. I'll talk a bit about one of them, the PESO project, which is the one that I'm the PI for going forward, which is a 5-year project funded at a reasonable amount to get, keep the efforts of ECP going. The other projects here, many of them, most of them, are focused on specific types of reusable libraries and tools. So OASIS is focused on math data and viz libraries. SWAS is on application services and workflows. S4PST is for programming systems. Think STEP is for performance tools. Colab is about training and workforce, and Corsa is about partnering with software foundations. So those are the other projects. So let's talk about PESO. So PESO is an aggregation project. It's focused on partnerships, partnering with the broader community, partnering with the other software ecosystem organizations, and we provide services, and we provide 2 major products, E4S. Again, this is post-ECP, so we are in charge of making sure that E4S is viable, continues to grow, continues to be available, tested, is easily usable by people. We provide some training. And also we contribute to SPAC. SPAC has many contributors, but we are one of the key contributors to SPAC as a facility and a usable resource for Office of Science application teams. And then we provide the port and test platforms, things like Frank, and a little bit in terms of better scientific software support. So PESO is an aggregator. We take, collect, and then send out value add to other efforts that are going on to the broader computing community. One of the things I want you to note from this in our organizational structure is that we engage in the PESO project many team members who are also part of the other post-ECP seedling or extended projects. And so if you look at in this list in the purple boxes, all of the people in this list are people who are also part of one of the other projects. And so it was our way of making sure that there's good communication through this one person in each of the other, or sometimes a few people in each of the other projects. We could assure that there was good communication across the projects. And so that was our organizational strategy for PESO. We are also in the process of creating a consortium. It has a name. It's called CAS, the Consortium for Advancement of Scientific Software. It's a federation of these organizations, the one that I just told you about PESO and the others. And it's meant to address this kind of aggregating of development efforts. PESO is one member of that. We have specific roles, and a lot of our activities in PESO are going to be in service of CAS. We're planning, for example, a collection of birds of a feather sessions in June. PESO is organizing the birds of a feather session. We're engaging the libraries and tool teams from the other software organizations, but we're sponsoring this as a CAS activity where CAS is the consortium. And this is just a leave behind slide of the goals that we have for CAS as we're going forward. And as I mentioned, we have the community BOF days coming up. Okay. All right. I think the last part of this talk is going to be focused on what we foresee as, some of the broad term impacts that we want to see from ECP investments. And I'm couching this in a phrase I call 100x. And why do I say that? Well, these are some slides from some of the ECP applications. I didn't handpick these. This is actually quite representative of all of the applications. But the numbers that are circled in the green ovals, these are speed ups that these teams observed from their activities under ECP. Some of this comes from the improvements of hardware, of course, but others of it comes from the reinvention of algorithms and implementations in software, and the combined impact of all of that is truly transformative performance improvements. And what we want to do is we want to expand that. We want to include that as an offering to teams, other application teams, as we go forward. And so, ECP investments enable this 100x improvement in capabilities. We took, over 7 years of time. It took a big investment, but we can now leverage that. We emphasize software quality so that what we have produced is more easily usable, well documented, well designed, easier to support, and easier to bring users in to take advantage of it. We've prioritized community engagements. We'll continue that. As I mentioned, the BOFs in June. We have these portability layers that are a credible way to get performance portability. And using ECP software, we can lower costs and increase performance for accelerated platforms. And really, outside of AI, industry is not caught up. So lots of our science apps are, if they work on GPUs, it's specifically to NVIDIA GPUs. And the ability to use GPUs from other areas, this is one key contribution that EC provided. And it's really allowed us a path and a software ecosystem for others to leverage. Also, there's more than one way to leverage 100x. Certainly, you can do it for the very high-end science capabilities, but it can also reduce cost. In fact, I think the long-term legacy of ECP won't necessarily be at the very high end. That's really important, no doubt. But it's going to be also at the low end and mid-range, where lots of teams are unable to realize performance, cost, and efficiency improvements from one generation of machine to the next because they're not working on GPUs. CPUs, many applications work on CPUs, but the performance and energy performance metrics of CPUs are not improving generation to generation. If you move to the accelerated space, you can see tremendous energy improvement, first of all, from just migrating from CPUs to GPUs, but also getting on these new commodity performance curves. And that, I think, is one of the biggest legacies that ECP will provide. We provide libraries and tools that help you. We also de-risk the path. We show that it's possible for a broad set of applications to achieve performance on GPUs. And not everybody was sure of that when ECP got started. It's now much more certain for a large set of applications because of the examples that ECP provided. Last thing I will mention in this space is that we did leadership science on leadership systems. What about AI and ML? We already have a bunch of AI and ML products in E4S. We can easily add and curate a larger set. In fact, we already are starting to do that. And so the bottom line for AI and ML is that extending what E4S provides is better than starting a brand new stack for scientific machine learning. In the cloud environment, we're already available in containers on AWS and in Google Cloud. We can extend this, going forward. Quantum, I already mentioned that we see that quantum is just another type of attached or accelerated device, and we know how to handle those kinds of devices. And so we see that the foundation that ECP provided in the software ecosystem is extensible in major ways that we foresee coming along. Okay, since this is about industry and agency communities, I want to leave the last few comments for this specific community. So we've had a tremendous engagement. One of the most delightful things about my experience on ECP was our regular interactions with our industry and agency council meeting. They brought new ideas to us. They brought enthusiasm. We got beautiful relations built out of that, and I'm hoping that those will continue. I'm hoping, and we seem to see that DOE more broadly values these relationships and wants these relationships to continue after ECP is over. And in particular with our agencies, NOAA, NSF, NASA, and DoD, we've been able to engage in multiple engagements and explorations of capabilities. And the last one I want to show you is from an effort done by the HPC Mod Office, and it's what they termed as a fast follower case study without any direct engagement from the ECP teams. They wanted to experiment with E4S. And so they had two phases to their effort shown here on the chart. And I want to just show you some results that were given by Sean Ziegler at the January 2024 meeting of the Industry and Agency Council, because I think they're really telling of the potential for our activities going forward. One is they were able to, because Flux is part of E4S and easily installed using SPAC, they could do a very simple installation script. They now have, for the first time, a new scheduler that lives in user space, that a user is able to manage a large collection of jobs, using a nice dashboard panel and a highly productive scheduler in a way that was never done before. And again, very easy installation. A second one is Tau. They've been widely users of Tau for a long time, but there's so many different installation options that are now possible because E4S comes with this broad set of SPAC installation parameters that they can take advantage of. The third is, for the very first time, they could install Cocos and Raja, these performance portability layers that they were unable to offer to their users before because of the cost of trying to install them and the support staff and the speculative nature. But now, because it's so easy to install them, they can provide them to their users, and they were able to install them and show, in the tests that came with them, some nice improvements in performance. And so they were working the way they were supposed to. And then the last example I want to show you is LAMPS. LAMPS is widely used by this particular user community. But they found that by using the E4S SPAC installation scripts, they were, again, very easily able to launch and install multiple versions of it. And not only that, what was really interesting is that because the LAMPS installation configuration parameters were provided by the LAMPS teams and carefully tuned by the development team, the key output from that was that the SPAC build. So they've been using LAMPS for a long time, getting a certain level of performance out of it. But the E4S build of LAMPS ran twice as fast as their own installation had. So not only is it easier to install, lots of different configuration possibilities, but it actually runs faster, twice as fast as what HBCM MP was able to do on their own. So we consider this to be a great success story and a promise of things to come. Okay, final remarks. We learned a lot about producing software contributions to the HPC community, how to plan, execute, track, and assess, integrate, and deliver, how to interact better with the broader HPC community, how to have better engagement with industry, agency, and international collaborators. In post-ECP, we propose to continue and expand these efforts, as I've described. And really, we intend to realize the potential of the ECP legacy across the HPC community. We want to realize this 100x potential, not just at the very high end, but also with accelerators at the low and mid range. And then also do that with a trustworthy and sustainable and cost-effective approach for our libraries and tools as we go forward. And we want to work with the HPC community to realize this legacy of ECP and beyond. We have a lot of new ways to interact and a lot of new opportunities to pursue. And thank you for your time.